Hey guys, welcome to video 3. In the previous video, we were able to optimize a portfolio with one constraint, which was that all asset weights in the portfolio sum to 1. Now let's look at a portfolio with additional constraints like specific return or beta requirements. But before we go ahead and code the solution into R, we first need to look at the mathematics behind the solution and how that will translate to code into R. The first of two mathematical concepts we'll need to review is the Lagrangian multiplier. The Lagrangian multiplier allows you to find the maximum or the minimum of a constrained optimization program. So if we look at our optimization program, here we still have our objective function, which is minimizing the variance of the portfolio, and we now have two constraints. The first constraint is that the weights of the portfolio sum to 1, and the return on the portfolio has to equal that of the mean excess return on the total market. The first thing we need to do is form the Lagrangian function, which is done by combining the objective function and the two constraints. Now that we've formed the Lagrangian function, we're going to work to find the solution of the constrained minimization problem by taking the first order derivatives with respect to w, lambda 1, and lambda 2. The result is the following three first order conditions, and the first equation can actually be rewritten in terms of optimal w, or the optimal weights. Now noticing that the optimal w is found also in equation 2 and 3, we can reinsert w star into the first order conditions 2 and 3, and we now have two equations with two unknowns, which is lambda 1 and lambda 2. When reinserting w star into the second and third first order conditions, we see something very familiar. The variables calculated in video 2, the AA, BB, CC variables that were somewhat obscure, are now found within the first order conditions 2 and 3. Knowing this, the linear systems can then be solved with matrix equations that result in the form in step 4. Once we've calculated the lambdas, we can reinsert into the first order condition number 1 to get the optimal weights. The thing to take away here is the matrix form you see in step 4, because this is closely going to follow the code that we're going to put into R. Lastly, some basic matrix multiplication rules we need to know. The syntax of matrices always starts with rows and then is followed by columns, or an m times n basis. This means the columns in the first matrix always must equal the rows in the second matrix, and therefore order matters when you're doing multiplication. And the resulting matrix is equal to the number of rows in the first matrix and the number of columns in the second matrix. Now the next step is to code this into R. Okay, we're back in R, and now we're going to calculate and plot three separate portfolios. First, M1, it'll be a minimum variance portfolio subject to the return being equal to the excess return on the market. And then M2 will again be a minimum variance portfolio subject to the beta of the portfolio equaling 1. And then lastly, we'll calculate the tangency portfolio, or the portfolio with the maximum Sharpe ratio. We'll start with calculating the portfolio M1, and we're literally just coding in the formulas we went over in the PowerPoint. We're going to assign the variable lambs to the two unknown lambdas we're calculating, and we'll again use the solve function, which solves a system of linear equations in matrix form, which again we did see in the PowerPoint. So we're going to create a matrix that's going to be a combination of the variables that we saw in the PowerPoint, AA, BB, BB, CC. And we're going to say that that matrix has two columns. And we're going to be multiplying that by our constraints, which is a 2x1 matrix. And the first constraint is that portfolio weights equals 1, and the return of the portfolio equals the excess return on the market. Now let's return that value and see if we get two lambdas. And you can see two lambdas have been populated in the console. Now that we've calculated the lambdas in step 4, we can reinsert them into the first order condition to calculate the optimal vector of weights. We're going to assign this value of W1, but first if we go back to the PowerPoint, we are just coding in this equation right here. So if we go back to R, assign our variable W1, and we're going to be multiplying the inverse of the covariance matrix times the first lambda subsetting to the first row times a vector of 1s plus the second lambda subsetting to the second row times our vector of returns from the 47 industries, which is our MUM variable. And then we'll return this value to see that we populated. And these are the optimal portfolio weights for a minimum variance portfolio, given that the return of the portfolio is equal to the excess return on the market. We are then going to calculate the average return of the portfolio by multiplying the optimal vector of weights by the average annual return of the 47 industries. Both of the matrices are 1 by 47, so based on matrix multiplication rules we went over in the PowerPoint, we're going to need to transpose one of them. We're going to assign this a variable mu1. We're going to transpose the weight vector, and we're going to multiply that by the vector of the 47 industry returns. And we're going to check that equals 19.27. Oh, I need to calculate this in. And that 19.27 should equal the excess return on the total market, and it is equal. Finally, we're going to calculate the standard deviation of the portfolio. We're going to assign this a variable sig1, and we're going to do this by using the known fact that the square root of the transposed weight vector multiplied by the covariance matrix, which is then again multiplied by the optimal weight vector, should give you the standard deviation of the portfolio. And let's make sure that populates. And you can see that's the standard deviation of the portfolio given the two constraints. We now move to portfolio M2, which is a minimum variance portfolio subject to the portfolio's beta equaling 1. The first thing we need to do is calculate a vector of betas for the 47 industries. And we do that by first assigning a variable, and we're going to do it through linear regression. And the function for that is LSFit, and we're going to run the regression of the daily returns of the total market, which is denoted as 9 plus 2. And we're going to run that on the daily returns of the 47 industries, which is denoted as returns subsetting from the second column to the number of industries plus 1. And from the regression, we want to return the coefficients. And from the coefficients, we want to return the actual betas rather than the intercept. So we want to subset this from row 2 down and execute that. We now calculate the lambdas as we did in the previous portfolio with one small difference. The vector of returns for the 47 industries and variables BB and CC must be replaced with the beta vector. So let's go ahead and change the variable names to represent beta. And we'll go ahead and change the return vector for the beta vector. And one more here. We can copy down the lambda calculation from the previous portfolio and just change the variables BB and CC as well as the constraints. So let's do this to represent the beta vector. And let's also change the constraints. The total portfolio weights still need to equal 1, but now we need to change this to another 1 because the beta of the portfolio must equal 1. We can also copy down the optimal weight, mean, and standard deviation calculations from the previous portfolio. We just have to be careful to replace the variable names and replace the bet vec wherever you see the return vector. And just to double make sure that our portfolio beta equals 1, let's multiply the beta vector times our portfolio weights. And you can see it returns a value of 1. So this has correctly constrained our portfolio to a beta of 1. This is the end of this video, but on the next one, we'll work to calculate the tangency portfolio, add these to our existing plot, and create a table to analyze all of our portfolios. Hope to see you there.